Good afternoon. My name is Nicholas Kaple, and I'm a junior in the Randall Research Scholars Program studying mechanical engineering. Today, I'm presenting my project titled Laser-Assisted Cold Spray Deposition of Refractory Metals. This project is supported by Dr. Luke Brewer in the Department of Metallurgical and Materials Engineering. To understand this project, we first have to ask the question, what is metal additive manufacturing and why do we care about it? So the easiest way to understand this is to talk about the opposite of additive manufacturing, which is subtractive manufacturing. In subtractive manufacturing, we take a bulk metal like this, bigger than the part that we want to make. We then cut away material and we end up with a useful part or component. On the other side, we have metal additive manufacturing, in which we take powderized metal, and then we add energy and reorder those particles. This gives us the useful part or component that we want to make. The second question is, what is solid state additive manufacturing? Again, we're going to first start with the opposite of solid state, which is melt-based additive manufacturing. In this case, we take a solid powder, and so in this case, we then add energy to that. So we're adding heat using a laser. That solid powder is then going to melt into liquid metal, and then by allowing that liquid metal to cool, we then end up with another solid bulk metal. So you'll notice here that we're going from solid to liquid, and then back to solid state. On the other side, we have a deformation-based solid state additive manufacturing process, where we take solid metal powder. We then add force to that, or we can then accelerate these particles to very high speeds. And then those solid metal powder particles are going to deform into a solid bulk metal deposit. You'll notice in this case that we're staying in solid phase the entire time during manufacturing. So some of the drawbacks of melt-based additive manufacturing are that we have a very high cost of equipment in operation. Also, melting and resolidification can lead to high tensile residual stresses. We can get elemental segregation, or we can get high porosity. If we're trying to process refractory metals like niobium, we have very high melting temperatures, and that makes it really difficult to process using melt-based. And also the material properties of our powder are going to be changed by melting, and so we have to normally do post-processing or heat treatment to get the properties that we want. In solid-state additive manufacturing, the material properties and microstructure of the powder are going to be largely unchanged during manufacture. We also have lower equipment requirements, so we can more readily adapt these methods for using in the battlefield or in other situations. We can also perform these processes in open air. We don't need an inert environment like we do with the laser. And we also have low heat input, which is going to limit oxide formation. Dissimilar metals that we couldn't otherwise weld together, we can mechanically bond using solid-state manufacturing. This is an overview of the laser-assisted cold spray process. We call it cold spray because we're not melting anything, but in fact, it's a very high-temperature process. So in this case, we start with compressed gas that branches off into two different branches, one of which picks up powder from a powder feedstock container, the other of which goes into a gas heater and becomes superheated and supersonic. These two streams converge again in the nozzle, and then this mixture of, we use helium here, super hot helium and powder, is going to then be sprayed onto a substrate, and we can build up a deposit. In our case, we use a laser, which generally improves mechanical characteristics, and that's going to be then impinging at the same point of deposition as the gas powder stream. So why is cold spray additive manufacturing a useful process for niobium in particular? Niobium has a liquidous melting temperature of 2,500 degrees Celsius, and so it requires an extremely large amount of energy to actually melt. Niobium also sprays surprisingly well using helium carrier gas, and we found in our work that we get low porosity and high deposition efficiency. Also, we found in other metals that the addition of laser heating can generally improve ductility and adhesion strength. We normally use niobium right now in applications in aerospace, like for supersonic weapons, hypersonic weapons, or in nuclear fusion reactors. And this here is a video from our lab of our process. You'll see here a plate with holes drilled into it. That's essentially the hand of a robot arm with the robot arm behind it articulating it. Onto that robot hand, we affix a substrate. We use a steel substrate. And in the foreground here, we can see a tube. That's where that supersonic mixture of powder and gas is, and it comes out and sprays onto the substrate. This work investigates two key knowledge gaps in cold sprayed niobium. The first question that we want to answer is, how well do cold sprayed niobium particles adhere to the substrate at different laser power levels? We want to move from a pass-fail criteria to using quantitative methods. So in the past, we've asked the question, have the particles adhered to the substrate? Instead, we want to answer the question, how strongly have the particles adhered to the substrate? The second question is, how successful can we be in spraying large, so greater than 3 millimeters thick, niobium deposits? Are there operational challenges involved? And are there adhesion differences between small and thick niobium deposits? So we in our lab use double-lug shear testing to evaluate adhesion strength. And so we start with a 4340 steel substrate. We then buy that material and machine it down to the dimensions you see on the left. We can then cold spray niobium onto that substrate. And from that bulk pad that you see there in the middle, we can then machine down into 2 different lugs. Taking this machined sample, we can then apply force to it. And so this is the lug shear process where you then basically apply force to those lugs. And at a certain point, we're going to hit such force that this niobium lug is going to pop off. It's going to become not adhered. And at that force, that correlates directly to the adhesion strength of the niobium lug. Preliminary microscopy from Madison Voida's thesis defense here at UA shows a generally good bond between niobium and the substrate. We can see here in the bottommost image of the no laser condition that we have very little porosity, no gaps in the image, and also pretty good penetration of niobium into 4343 substrate on the bottom. In the other laser conditions, increasing in laser power, we generally see a decrease in porosity and an increase in penetration depth of niobium into 4340 substrate. Before lug shear testing can proceed, however, we have to solve a few delamination issues. We found that when we're spraying thicker deposits, so in this case we have about 1/8 of an inch thick deposit, we found that we can sometimes get delamination between niobium pad and 4340 substrate. And you can see it here in this image circled red. Covering in our group. And the material properties of our base powder are going to be largely maintained during processing. Initial results indicate that cold sprayed niobium deposits fairly well onto 4340 steel. We have low porosity and relatively good penetration into the substrate. In addition, thick deposits of niobium can lead to delamination of the deposit from the substrate. So we have to perform some more work to figure out what's causing these issues. These are my references. Are there any questions?
What other metals that are commonly used with the cold spray process?
Oftentimes we see refractory metals like niobium are pretty common, but more commonly you'll see in the aerospace industries like aluminum is very commonly used. Aluminum is very easy to cold spray. Oftentimes too you'll see sometimes ODS steels, oxide dispersion strengthened steels, and those are also kind of a broadening piece of the research in this field.
I was wondering, are there any other ways to create parts with cold spray besides spraying a pad onto the metal bar?
Yeah, one way you could do that, that's also being used more and more now, is you can create tubes by essentially taking aluminum bar, spraying onto the aluminum tube, and then you can dissolve away the aluminum. So using oxide dispersion strengthened steels, like I said, that has like a nuclear reactor application. And so you can create tubing essentially by using the cold spray process.
Is the cold spray process commonly used in industry?
Generally, the biggest use for it right now is in the aerospace industry. There's a lot of work that you can read from like Boeing and other industry giants. So far, the goal for us is just to increase the knowledge base around niobium in particular, and so far that's not super investigated in the industry.
You mentioned that part of your goal is to get larger sizes above the 3 millimeters. What cause do you want to go larger? What issues were you having with these smaller amounts of niobium?
There's not an issue with smaller amounts, but our goal is to basically create an additive manufacturing process. And so to create actual parts, you have to have a much thicker deposition thickness. It's really easy to do just very thin coatings, but when you want to create actual bulk parts, you generally just have to have a much thicker deposit. So that's what we're trying to solve.